Hi everyone, this is my video number 26. So we have about 2 weeks to go. So within these 2 weeks time period, I will give lectures on Fourier series, Fourier transform, Laplace transform, and Mellin transform. And I have also uploaded the notes, earlier than in the Putra Blast. So these notes. So to make the time short, I just read from these notes all those detailed formulation, where the part that I need to prove, then I need to write, then I will do the writing form. Okay, so I hope you have downloaded this notes as well as printed out, so that's easy for us to discuss on the material. Okay, so let's begin this notes, this lecture. So first I'll talk on the Fourier transform. So first thing is the definition of the integrable function or absolutely integrable function. We say a function of x is absolutely integrable if satisfy that condition. We say fx in LP of domain omega if we integrate over those domain of fp absolute of fx to the p less than some is bounded. Okay, so there are typing error there. So there are many typing error in your notes, so please be aware of this thing. And then those have a theorem. Next we have a theorem there. So this theorem is you can look the proof in the book by Snedden, the use of integral transform. So we suppose that fx and its derivative is continuous on R except at a finite number of points, for which f has integrable bounded discontinuities, and ft is absolutely integrable function in R. So based on that definition, so the Fourier integral transform state that for the discontinuous at x at t equal to x, so we can split this from positive part and the negative parts, and given by this formula number 1. Okay, and if f is continuous at t equal to x, so which means fx where x from positive side, x from the negative side, they are equal, so that we have 2, so they give you fx on the left side. Okay, so next we go to the definition of Fourier transform. So maybe some of you are quite familiar with the Fourier transform. So the definition is given by that, and the inverse is given by that. So I can write here the Fourier transform of fx. Fourier transform of fx is given as, we write f of x as 1 over square root 2 pi from minus infinity to infinity fx e minus isx dx. Okay, this is the Fourier transform, and some authors just use fs, and some use that, and there are many other notation as well. And for the inverse Fourier transform, inverse Fourier transform, where we can find fx is defined as 1 over 2 pi integrate from minus infinity to infinity fs e isx ds. Okay, and if you look at the notes, here, again we use half fx positive, fx negative. So here negative should be inside the bracket. If x is continuous, so if f is continuous at x, So we have basically this just give you fx. Okay. And then, as I mentioned earlier, that different authors may use different notation of Fourier transform, and also this part is on the notation of fs of fs. Some authors using that, and this for the inverse of Fourier transform is from here. I can also write this fx as f inverse of f of s. That will give you the inverse of Fourier transform. Okay, so now the basic property of the basic properties of the Fourier transform. I list here 5 basic properties. Of course, if you refer to other references, we may have some other properties, which is I'm not going to prove all of this. I will prove number 1. I think 2, 3, 4, and 5 you can prove that. It's not difficult to prove. So let's prove number 1. For number 1, we want to prove that fx minus a s, this is equal to e minus as integrate minus infinity to infinity, so fx we want to prove this is e minus isa fx. Okay, so we use the definition for that. So Fourier transform for function fx minus a, this is 1 over square root 2 pi minus infinity to infinity. So we have fx minus a, then e minus I sx dx. Okay, if I use substitution, let's say u equal to x minus a, so we have du is equal to dx. Okay, you can also write x in terms of u. We have x equal to u plus a. So if you substitute into there, so we have 1 over square root 2 pi integrate minus infinity to infinity so we have here, this is fu, so e minus is, your x is u plus a, and our dx is du. Okay, so I can factor out eisa, so that gives you 1 over square root 2 pi. I can factor out because it's free of u, so those e minus isa, the rest is minus integrate from minus infinity to infinity fu e minus isu du. Yeah, so I can write this part here as here, can put it there. So you can see this is the u is just dummy variable. Yeah, u is just dummy variable, so I can write this as a e minus a as f of fx s. So that's as what we want to prove. Okay, so that's the properties, the first properties, and then the rest you can prove by yourself. Now let's go to the first theorem, and then on the Fourier transform. If fx satisfies the condition of Fourier integral theorem, so you can see what is the Fourier integral theorem, which is fx is continuous, bounded, and so on and so forth. And then the Fourier transform of fx is bounded for all s, and fs is continuous. Again, typing error there. Fs is continuous for all s. The proof of part 1 is not difficult, yeah, to prove the boundedness of Fourier transform. So if you take the magnitude of fs, all right, this is from the definition. You take the absolute value of those. This will be less than that part and that part, and we know this part is bounded. If you take the absolute value of that, so that's bounded, and then the rest is just left with that. And this also, since f is absolute integrable function, so all these are bounded. So that's proof for the first part. Yeah. To prove the second part, the continuity of Laplace transform, so if you take the difference between some small number h, some small number h, we have f s plus h minus fs. Yeah, we take the difference between those two. This, by definition, this is 1 over that minus infinity to infinity. So we have here fx e minus I, our s is s plus h x dx minus that 1 over those things, integrate minus infinity to infinity. We have fx e minus I sx dx. Yeah? So you can factor out those. You can factor out those, okay, and then minus infinity to infinity. Oh, I forgot those absolute value there. Then absolute of 2 pi, we have again 2 pi because it's positive, and for that you can factor out those. So we have this less than. Yeah, when you change the absolute, bring into inside the integral, we have less than. So for that we have fx. You can factor out fx. You can factor out what, e minus I sx, right? What left is e minus I sh minus 1. That correct? Yep. Dx. Okay. And this is again less than 1 over those things, minus infinity to infinity. So we have fx. We have e minus I sx. We have e minus I sh minus 1 dx. Okay, then we know that this is bounded. F is absolute integrable. That part is bounded, so we can write this as a square root 2 over pi and some constant m. And whereas for that part here, you can take the limit because we consider at as h is small. So if you take the limit as h goes to 0, take the limit h goes to 0, e, this is should be minus here, minus I sh minus 1, that gives you 0, because h goes to 0, that gives you 1, 1 minus 1, you got 0. So for all x in R. So therefore we have, if we take the limits of h goes to 0, f s plus h minus f s, okay, that will give you 0. So therefore we can conclude that f is continuous. Okay, so that's the proof given in the part 2 there. in your notes. Okay, I just write to, hopefully that will be more clearer when I write those things. Hopefully it's not clear. Let me focus those. Yeah. Okay, and then so this is the end of the proof, and this is the other parts. If f(x) is continuously differentiable and f(x) goes to 0 as absolute f of x goes to infinity, then we have this result here. And again, it is not difficult to prove. You just change f using the definition of Laplace transform, Fourier transform. Okay, so you can write those. We want to prove f prime x s equal to ISFS. Okay, if you use the definition of Fourier transform, f prime x s, this is just 1 over 2 square root 2 pi integrate minus infinity to infinity. So we have f prime x e minus ISX dx. So you can evaluate this. You can integrate this by parts. So integrate by part. Integration by part. Yeah. Where you can consider u as e minus ISX. That gives you du is minus ISX. Minus IS e minus ISX dx, and you can consider dv equal to f prime x dx. Okay, so if you substitute all this into if you use this integration by parts for that, so you have you can easily see that this is equal to IFS. And when you substitute, then also you also need to use the given properties there, that fx, you need to use this in order to evaluate those things. Fx goes to 0 as x goes to infinity. Yeah, so you can have that result. And then if fx has a jump discontinuity at x equal to x naught, then the Fourier transform of f primes, f prime, that's the Fourier transform, the definition of Fourier transform. And then we split at the singular points. So we have along r, we have along r, this is the x naught. So we integrate from minus infinity to x naught. Now this is the singular point. Plus x naught to infinity. So means we split into two, that part and that part. Okay, so we split that, and then we know that this is for other part we have ISFS. This is given previously, that, and this is for the at the singular point where we split those x approaches x naught from positive, x approaches x naught from negative. So we have those results. Okay, we have example here. The example is quite lengthy, so I think I continue the example in the next video. So for this video I'll stop here. Okay, bye bye.